Maybe I'll use the computer.
So, welcome back. Now we resume with accelerator-related topics. And now it's Chris who's leading us in the world of cooling. And today is solenoids, optics plus cooling, 1 hour.
Okay, so
No,
1 hour or
45
45
minutes,
45.
sorry.
Yeah. So what I'm going to do, I'm going to talk for 45 minutes this morning, and also I will continue tomorrow on solenoid optics and cooling. So I'm just going to see how far I get through it, and then depending on how far I get through, we'll have more or less tomorrow, and then we'll see how we go. So, okay, so in ionization cooling systems, most of them use solenoid optics to focus the beam. So what I'm going to do, I'm going to start off by going through the optics for solenoids. So I went through quadrupoles. I went through quadrupoles on Monday briefly. So I'm going to go into solenoids this time, where things are slightly different, as you will find out. I'll go through the optics for solenoids, and then if we have time this morning, I'll go into how that affects emittance and ionization cooling. If we don't have time this morning, then that's absolutely fine. I'm sort of expecting that to be tomorrow morning. But we'll see how it goes. So what we want to do then, in the first instance, is we want to get to a transfer matrix for the solenoid, just like we did for quadrupoles before. And just to remind you what the transfer matrix is, so you have these you have these transport properties. You have the transport of the beam. So you have the beam, the particle position at some point 2 is a transfer matrix times the particle position vector at some point 1, where we're talking about the phase space position. That means the position in momentum and physical position space. And so for this one, I'm going to use position as one of my phase space variables, but I'm going to use transverse momentum as the other one. And on Monday I had angles. Today I'm using transverse momentum. And just for your information, I won't go into it much. We'll refer to it, but I won't do any maths with it. This is actually the first part of a perturbation theory. So this is like the linear part of a perturbation theory, but there's a quadratic part and a cubic part and so on. So you can write down that the position at point 2 is a linear superposition or linear operator on the position at point 1, plus a quadratic operator, plus a cubic operator, and so on. And so in the full Hamiltonian, in the full formalism, one goes up to higher orders, and we have a transfer map based on tensors and things like this. So I'm just going to go to the first order though for this talk. So, and the other thing I'm going to do differently is I'm going to use Hamiltonians for this lecture. So if you're not familiar with Hamiltonians, many will be, some maybe aren't. So I'm going to try and introduce it gently. So that the Hamiltonian is, which is typically written with the letter H, is an expression of the energy of a system. And so for a Hamiltonian, we have the equations of motion. So for example, the position, change in position as a function of Z. I'm going to use Z, so longitudinal coordinate as my independent variable, my integration variable, is equal to partial derivative of H with respect to by px. So dh by dpx, partial derivative. Oh, I missed the sign. So there's hopefully I'll fix that later on. Sorry, I'll fix that offline. So there should be a minus sign here. So then in momentum, you have the same relationship, but it's minus partial derivative with respect to x times h. So these are the equations of motion. So I'm going to go through an example to start with. There you go. I got the sign right here. I'm going to go through an example now for a simple harmonic oscillator, and I'm going to derive a transfer matrix for a simple harmonic oscillator. So we start with the Hamiltonian, and it's got 2 terms of the Hamiltonian. So it's got a kinetic energy term and it's got a potential energy term. So the kinetic energy term is half mv squared. So classically half mv squared, px squared divided by twice the mass. And then the potential energy term is like for a spring, stretch spring, it's the spring constant times the position squared. And then the equations of motion is partial derivative with respect to px of the Hamiltonian, which if we do the maths is just px divided by m. So the 2 comes down, we get px divided by m. And then then for the change in momentum with respect to time, because here I have time as the independent variable, we do again partial derivative with respect to x. We got the minus sign there, so we get a minus kx. Right. Okay. So as I say, there's nothing special about a particle accelerator, and we can define the transfer matrix for our oscillator just using these formulae here, and we can get a transfer matrix which is just so the position at time t plus dt or z plus dz is equal to the identity matrix plus this derivatives. So these things up here times dz, and this just comes from the sort of definition of the derivative. And this is the transfer matrix which takes us from a point at z to a point at z plus dz. Okay, charged particles are a bit more complicated. So that's kind of simple harmonic oscillator. So now for transport through charge, transport through a field, this is the for this transverse phase space vector x px y py as a function of z is the independent variable. The Hamiltonian is given by this expression here. So a couple of things to note. So this is actually just the mass shell condition with h being pz or very close to it. But the slight difference is that we use canonical momentum here, and canonical momentum is related to the kinetic momentum, just with a difference of charge q times the vector potential, magnetic vector potential. And so if you just square out the brackets, you get e squared minus m squared minus transverse p squared, and this looks like pz. Fine. Right. So then the next question is, what's the vector potential? Okay, so if you remember your electromagnetism, there are some experts in the audience, I understand. So the vector potential is given by the line integral around a circle is equal to the magnetic field passing through a surface. So here's our solenoid. We have magnetic field lines which are going like this. So if we draw a circle going around the magnetic field lines, then the vector potential will go azimuthally around the field lines, and we can say so in a uniform solenoid, the field enclosed on the surface goes with radius squared. It's the area of this enclosed surface, and the length of the circle goes with radius. So we get a vector potential which is proportional to distance from the center of the solenoid. Okay, and so that's what's written. That's what comes out here. I've done it in Cartesian coordinates because we're in Cartesian coordinates. So the vector potential here is just the vector potential going around that circle, where B0 over 2Q is the the magnetic field strength, and I've divided out Q because we want Q to drop. We want Q to drop out later on. So I've just taken B0 as magnetic field divided by the charge of the particle. Fine. Good. Okay. So let's plug that vector potential into our equations. And see where we end up. So if I take the horizontal vector potential, I put it in here. Again, I want the Q to drop out, which is why I put the Q in the vector potential expression. this B0 is just BZ divided by Q on the axis. And then I plug this one in down here, then we get this expression for the Hamiltonian. Okay. So we're getting there. So the other, so what we saw for the simple harmonic oscillator example was that the transfer matrix is related to the quadratic terms in the Hamiltonian. So terms in x squared and terms in px squared. So somehow what we want to find to get to the linear transfer matrix is we really want those quadratic terms. So here so somehow this square root makes our life harder. So we want to get rid of the square root. We do that using the binomial expansion. So we can multiply out these brackets. We put a P0 at the front, and then divide through by P squared on all of these brackets, just to get rid of this constant. Then actually it looks just like the binomial expansion. So just to remind you, P0 squared minus M squared, that's P squared. And so we can have P squared minus Q, oh, I got rid of that. P squared minus Px plus Y B0 squared. I won't do the other half of it. Square rooted, take the P out the front, that goes to 1. This divides by P squared. And then it looks just like this binomial expansion. And so we can multiply it out, and then multiply out the brackets, and we end up with this expression for the Hamiltonian. And so the reason this is neat, the reason it's quite nice having these doing it in the Hamiltonian way, is that actually once you get to this point, you can basically read off the transfer matrix terms. So the partial derivative with respect to Px gives you a 2 times Px here, 2 times Py here. So those are the linear terms. And the partial derivative with Py gives you an x term, or the partial derivative with respect to x gives you a Py term, and so on. So let's go through it. So we have a Px squared plus Py squared. I'll just go through one of them, I think. Divided by 2p. So if I take the partial with respect to Px, then we get a 2 times Px over 2p. We got another one over here. Let's see if I got it right. And we don't have any more over here. So this here is dx by dz. So then if we're looking at our Hamiltonian, we have x at z plus dz is equal to x at z plus dx by dz times dz, okay, where we've calculated dx by dz over here. So we can plug this in. So we've got plus px at z over p. Let's see if I got that. Plus b0 over 2p times over 2p times y at z. So now if we want to write this down in terms of a first line of our transfer matrix, for example, we can write x is equal to, I guess it's the first column, is equal to we're going to get a 1. We're going to get a 1 over p. We're going to get b0 over 2p here. We're going to get a times dz. And we're going to get a 0 here. Okay, so this is how we're sort of filling out the transfer matrix. So this term's going to here and so on. And then I even look, there you go. I even got it right. Well, let's see. So the identity matrix is a given. So you got all of these ones across the identity matrix. But then you have this delta matrix times dz. Good. Okay. So then in the end, what you really want to do is you want to know the transfer matrix through a long set of solenoids. And so we can actually integrate this system. There's a sneaky trick. So once you know the this delta matrix, you can actually calculate the transfer matrix. You can integrate out the transfer matrix. So if you just have if you once you know this. Once you know the delta matrix, so you know you have some transfer matrix at M, you don't know what it is, but you kind of want to know that the differential equation which lets you calculate the M as a function at a position Z. Well, this is just equal to M plus delta M. Subtract this off, and you've got then you have this expression here. Take the dz down to this side. So this is dm by dz is equal to delta times m. And that lets you integrate. The initial condition is that your transfer matrix from 0 to 0 is the identity matrix. So that's your initial condition. And once you have that, then you can integrate this expression out. Okay. So how are we doing? So there's a couple of other features. If you remember the definition of the conjugate momentum, the canonical momentum, you can actually turn that into a shear operation, so that the kinetic momentum is equal to the canonical momentum, I'll get the sign wrong, so I'm going to have to flip up to make sure I get the sign right, because I can't remember signs, minus QA. Good. Minus Q AX. So this is so once we know what QAX is, I'm just not sure about the sign there. So, but this is just a matrix operation. And so we can write this down as a matrix, just like this. The dz shouldn't be there. Okay, and then we can. So I'm not going to go through this derivation of the decoupling transformation, but I note that there's a decoupling transformation which lets us rotate, which defines a rotation, which will actually move us into a decoupled space where we only have 2D transfer matrices. That's something which is interesting, but I'm not going to go through that derivation. Okay, so what I want to say is I'm not going to go through the derivation of the decoupling, but I want to explain physically what's going on when you have a beam going into a solenoid. So here's your solenoid again. Have a magnetic field like this. So if you have a particle coming in, here's your particle. It's going to go through a superposition of a radial field and a longitudinal field. You have radial field component, so you have a radial field component, and you have a longitudinal field component here. So so if you imagine the forces acting on this particle as it comes into your solenoid, the radial field component is going to give it a transverse kick. So it's going to give it a kick into or out of the board. Okay, so I'll just redraw this. So you have a radial field component, you have a particle moving with longitudinal momentum, and so you end up having a kick in the azimuthal direction. So as particles go into solenoids, they pick up angular momentum. And it turns out that angular momentum, there's a canonical angular momentum, which is a conserved quantity, which is the so the canonical momentum so this is a conserved quantity. So what that tells you is you go into the solenoid. If it's a stronger solenoid, there's a stronger radial field, so you get a bigger kick. So that means that the canonical momentum component, the field component of the canonical momentum is stronger, so you end up with more angular momentum, but the canonical angular momentum is conserved. So if you have no canonical angular momentum going into your solenoid, you'll have no canonical angular momentum inside the solenoid, because there's the stronger field which sort of which sucks up the extra field component of the canonical momentum. Okay. Right. Again, I'm going to skip the derivation of the full derivation of the evolution of the beta function, but it's interesting to note that so you have this expression for the evolution of the transfer matrix, and you may remember last time I gave this expression for the for the transfer matrix in terms of these twist parameters, alpha, beta, gamma. So again, what one can do is actually plug this transfer matrix in here and use this differential equation to derive a differential equation for beta. And so you end up with a differential equation like this. It's actually very similar to the one for quadrupoles, but the only difference is in solenoids, you get an angular momentum term out here. So this is the canonical angular momentum in some normalized coordinate system. Okay. So we can solve this differential equation. Again, I'm not going to go through it. But so this is the differential equation up here. So if we put Fourier harmonics into, just consider a solution of beta as Fourier harmonics, if B square, or if B is a set of Fourier harmonics, then we might expect beta to be a periodic function of Z as well. So if we have B is a set of Fourier harmonics, then we can solve this equation with beta as a set of Fourier harmonics. And you get this expression out here, where Q0 is the average magnetic field strength, and Qn, these are like the harmonic content of the magnetic fields. Okay. Right. So some plots. Okay. So we have so this is an example of a cooling cell lattice. So we have the solenoid magnetic field, Bz, so the longitudinal field component as a function of Z. And in this example, it's a perfect sine wave. Okay. So the focusing strength goes with Bz squared. So this will also be this will be sine squared. And then what we find if we look at the solutions for that differential equation for beta, you end up having something which looks like this. So this is a function of P, momentum. So the features to note, so blue is beta as a function of P at the focus here. I also show in green beta at the anti-focus. So beta at the focus goes to 0 at some point. Beta at the anti-focus goes up to infinity at some point. What's going on? If we come back to this, you get interesting points here where n, so that's just some integer, n squared minus q0, when that goes to 0, this expression goes to infinity. And so what that means is the lattice is unstable. So in this case, the solenoid is actually over focusing. So there's so much focusing that it actually means that it's actually over focuses the beam and the beam gets lost. And so you end up with this what's called a stop band here, where the phase advance is 2 pi, and the thing becomes resonant and the beam's lost. So so this is the beta function as a function of Z here. So you have a focus at this point, another focus at this point, and an anti-focus at this point. Okay. So what I've done now is I've just messed things around a bit. So this is my harmonic. These are the harmonics which I'm putting into the lattice. So if I just go back to this one, so I only have a first harmonic here. I have a first harmonic with a value of 7.9. So that means it's a perfect sine wave. What I'm going to do on the next slide, I'm going to add in another harmonic. And so what that does, so you still have the resonance down here, but now because we have the extra harmonic, that's going to introduce another resonance over here. And that's because, coming back to this expression, we've now added in another harmonic Qn. So that means before this was 0 at that second resonance point, and now it's non-zero. So now we can actually have another n. And so this is actually it's actually a pi resonance now, pi mode resonance. And this is actually the lattice which we're planning to use for the demonstrator. Fine. Okay, I wanted to just put this plot up about tune. So there was a Tova, I think, asked on Monday about how tune can change with distance from the axis. Okay, so this is again the demonstrator lattice. It's fallen off the bottom. Doesn't matter. So it's lost the horizontal axis. I wonder if I can bring that back. Right. Sorry, it lost the horizontal axis. So let me bring that back. So this is the tune. And in fact, the way I've changed the tune in this plot is I've actually changed the momentum. So dark blue is 150 MeV over C, 1.15 GeV over C, and dark red is 0.23 GeV over C. So that means this one's more strongly focused, so the tune is higher. There's more focusing. This one's more weakly focused, so the tune is lower. If you imagine that you have a beam with like a squillion GeV over C, just like really massive energy, it will just fly straight through the magnetic fields and it will see no focusing at all. So you know, as you go to higher energy, the tune will you should get less and less focusing. Now, what happens is as you walk off the axis, so this vertical scale is distance from the axis. So I start a particle just right next to the axis here, and I calculate the tune of that particle, and you can see it sort of scales with momentum. If I start a particle a little bit further away from the axis, and I can calculate the number of oscillations, I just count the number of times that particle crosses the central part of the beam. So that's how I calculate the tune. I don't do anything much cleverer than that. I'm just counting the number of betatron oscillations per cell. And what you see is it's actually getting stronger focusing as you move off the axis. Now, the reason for that is somewhat complicated, but it's because the field is not uniform across the solenoid. So in a real solenoid, you have fields which vary across the radius. So the particles on the outside of the solenoid, which are crossing right out here, actually tend to see more focusing than particles which are just oscillating near to the center. The particles which are, so if you have a particle which is doing big oscillations like this, it sees more focusing. If you have a particle which is staying near the center, it sees weaker focusing. So I tried to draw it so that the tune's less for the particle near the axis. And so that's why you get this curvature. But you also see there's some other features. It's quite interesting, actually. There's a lot of substructure on this plot. So out here, things go a bit crazy. And that means that the particles are not really well contained. So they don't really have a very well-defined tune. They're sort of in a region where probably the motion is chaotic. Okay, three-body problem. Down here, well, that's interesting. Look, those particles are sort of getting stuck on one of these integer resonance lines. So these dashed lines correspond to whatever, 1/9, 1/8, 2/7, 2/6. I can't read it. But these lines correspond to the integer resonances I was talking about on Monday. And you can see that you get weird things happening, like this one's getting stuck as you move out. It likes being on this 1/9 integer resonance. This one here, it's getting stuck, and it likes being on this 1/5 integer resonance. It's interesting, isn't it? So there's quite a lot going on. We've got 5 minutes left. Okay. Let me see. So I'm going to start talking about moments and moment transport. So what I want to do next is I want to talk about emittance, beam emittance, and I want to try and make you believe that beam emittance is a conserved quantity, which I said on Monday. So let's try it again. Let's go through some of the details. So we're going to talk about, or should I go to questions? What do you want? Should I stop here and go for a couple of questions? We have questions this afternoon. I'll keep going. I'll keep going. So okay. So the moments of the beam, you know, of course, the mean, first moment, the variance, like the standard deviation squared, which is the second moment, and so on. So they're defined for some beam with a PDF H. They're defined by this integral. We can because a beam is not a continuous medium. It's actually made of discrete quanta. We can actually use the discrete version of a moment. So I'm going to assume my beam is running along the center of the beam line. So I'm not going to talk about. I'm not going to subtract off the mean. I'm just going to so for a moment, it's like a second moment will be, so variance in x, for example, is x squared. So I can write that down. Like this. So that's the second moment. It's a variance in x, and I'm just going to write it out. I'm just going to be stupid. That's x times x, okay? And it's just the sum over all particles. So if that's the ith particle, we sum over all particles in our distribution. Probably familiar. But we also have, which may not be familiar, the covariance of x px, which is also a second moment. And this is also the same thing, but it's the sum now of x times px. Okay. So now if I write down, I'm going to then take my phase space variable. I'm going to just write a generic phase space variable. So the covariance of u1 and u2 is just going to be, if I can write straight, sum of u1 times u2, where 1 refers now to the, I run out of indexes. So that means so this is now, this index here, I'm using that to denote that it's the first phase space variable in my vector, and it's the sum over all particles, and this is the second phase space variable in my vector. So if my phase space vector is x px, then these two things are the same, okay? Because the first element in my phase space vector is x, second variable in my phase space vector is px. Right. So what I want to talk about is how we transport an entire beam now. So using the transfer matrix, how do we transport the entire beam not just individual particles. And that means transporting these moments around the place. So moving the mean, moving the variance of the beam. So if this is my covariance at some initial point, well, I can just use the transfer matrix to move each individual variable. So the way I've done it here, I've written the transfer matrix out. M is an element in the transfer matrix, and I'm just going to take this. So I use the square brackets to mean sum over all particles. Sorry, the angle brackets mean sum over all particles. And now what I'm going to do is I'm just going to write out the transfer matrix, but we're using individual matrix elements. And so this sum is over the jth part of the transfer matrix, j1th, and this sum is over the j2th part of the transfer matrix. So this is exactly the same as the transfer matrix expression, transfer matrix definition, which I used right at the start. I'm just writing it out as in terms of matrix elements. And so the variance, the final variance is equal to the transfer matrix times u of the initial positions. So then if you remember back to your definition of matrix multiplication, one can explicitly write the matrix multiplication in terms of these elements. And actually what you see is this here is the matrix transpose. This is the matrix of this covariance matrix. So the final covariance matrix is equal to the transfer matrix times the initial covariance matrix, V. Right. So I'm going to define a covariance matrix. So the covariance matrix is the matrix of covariances. So fine, so it's a matrix, and the ijth element is equal to just this covariance of the ijth part of the phase space vector. Right, I'm going to leave it there. I'll keep going tomorrow. Okay, thank you.
So if you have a solenoid focusing a beam, almost like a lens down to a point, it hits that point and then it diverges, right? So if you have a series of solenoids, is the reason that that can focus the beam more at the end because we have the absorbers at that vertex, or can a series of solenoids, am I just not understanding how that works in terms of the divergence later?
So if you have a, so the absorber has nothing to do with focusing.
Okay.
So let's not think about the absorber at the moment. You have a solenoid, and you come down to a focus. What that means is that you're increasing the momentum spread of your beam, and you're decreasing the position spread of the beam at that point. And that's just the action of the solenoid as the beam's spinning round. It's getting this focusing force from the solenoid. It's completely independent of the absorber.
Well, I think that makes sense for me in terms of one solenoid. But then if you have, say, 10 solenoids in a line, and then you have the beam going through and it focuses down to like, big momentum spread, small position spread, and then it diverges, and then it hits the next solenoid, does it just like after the 10th solenoid, do you just get a really, really big momentum spread, really, really tiny position spread, or why does it change
It depends.
for multiple?
It depends on your lattice.
Okay.
Emittance is conserved, so one can develop a lattice which successively focuses more and more tightly, as long as you allow emittance to be conserved. You might find you need stronger solenoids as you go down to get more and more tight focusing, and then gradually less strong solenoids as you go further through.
Thank you.
Okay.
Okay, any further question for now? Don't see any question. So I invite you again, use the sheet in case you want to write down. We get to you tomorrow again, correct? Okay. So thank you, Chris. And we now connect it off.